So people, they might not like the quotient rule, but one of the things they start to do is overusing the quotient rule. Anytime they see a fraction, they start using the quotient rule, and the fact is, you only have to use the quotient rule when necessary. If there's ever just a single term on the bottom, or if you realize that it's just a constant multiple, most likely you don't need to use the quotient rule. And my good rule of thumb is, if I don't need to use it, I don't use it. I'll use simple divisions and simple derivative rules if I can. So let's look at this first one on A. It says find the following derivatives. You have x squared plus 4x all over 5. Well, really, isn't this the exact same as the derivative with respect to x of, really that's just a constant multiple, isn't it? 1/5 times x squared plus 4x. Or if you want to distribute it, this would be the derivative with respect to x of 1/5 x squared plus 4/5 x. Isn't that really what it is? And so we don't need to look at this as a fraction, even though, yes, it is a fraction and you can write it like a fraction. It is just a constant multiple. So finding the derivative of this isn't too difficult. So the derivative of 1/5 x squared, well, that would be 1/5 times derivative of x squared is 2x. Plus we'd have 4/5 times the derivative of x. Well, the derivative of x is just 1. So what do we really have? We would have 2/5 x plus 4/5. We could write this in numerous ways. I'm perfectly happy with it written that way. Another way you could have written this is 2x over 5 plus 4 over 5. Or you could have even said it has a common denominator, so you could have said 2x plus 4 all over 5. That's totally up to you. I don't care how you do it. I'm happy with the one that I boxed. Less work for me. The quickest I can get to the final answer, I'm happy with it. So I would have kept the one in the box, but any of those could have been possible answers. Same thing on B here. You're looking at the derivative with respect to x of 3x to the 4th all over 4. Well, that's the same thing as the derivative. Sorry, I have to write d dx because I haven't found the derivative yet. The derivative with respect to x, really that's just 3/4 times x to the 4th. So if you don't pay attention, you would have used the quotient rule here. High being 3x to the 4th, the low being 4. You would have done low d high minus high d low over what's below squared. No need to do that right now. Okay. We can just use the constant multiple rule. So what's the derivative of 3/4 x to the 4th? Well, it's a constant multiple, so that's 3/4 times the derivative of x to the 4th. Derivative of x to the 4th using the power rule is 4x cubed. So look at this, 4 times 3/4, the 4 simplify, and you're left with the final answer of 3x cubed. I want to note right here, notice I did write d dx on the first line, and then I stopped writing d dx on the next line. This first line with the d dx indicates that I still need to find the derivative. When I removed it is because I've actually at this point in time found the derivative. So I am able to put equal signs here. I have found the derivative, so I removed d dx. If you wrote d dx at the beginning of that second line, it would have been incorrect. Your work is not true because you've already evaluated the derivative. So be very careful with what you're writing. Let's go ahead and look at those next examples here. It says rate of change of systolic blood pressure. As blood moves from the heart through the major arteries, out of the capillaries, and back through the veins, the systolic blood pressure continuously drops. Consider a person whose systolic blood pressure, P, in millimeters of mercury, is given by P equals 25 t squared plus 125 all over t squared plus 1, for 0 less than or equal to t less than or equal to 10, where t is measured in seconds. So this is their systolic blood pressure over a 10-second period of time. At what rate is blood pressure changing 5 seconds after the blood leaves the heart? So they want us to find the rate of change at 5 seconds. We're finding a rate of change at a specific single point in time. And remember, a single point in time means I need to know the derivative. If it was an average rate of change, I'd have 2 points and I'd just find the slope between those lines. But here it's a single point in time, so we have to find the derivative and plug in the value that they've given us. So in this case, we need to find the derivative of p with respect to t at t equals 5. And I wrote this specifically because I wanted you to help with units. Remember, the numerator, P, is measured in millimeters of mercury. mercury, and the time is measured in seconds. And remember, any real-world problem, we need to label our answers. So this is going to be in terms of millimeters of mercury per second. Okay, so let's go ahead and work on finding that derivative. The derivative is 25t squared plus 125 all over t squared plus 1. You might want to think of trying to factor and simplify on this one. I do see that there's a 25 in common on top, but then it would be t squared plus 5. It's not going to simplify at all. Because it doesn't simplify, we have no option but to use the quotient rule. So let's think about this. What's the low function? The low function here would be t squared plus 1. What's the derivative of that low function? Well, the derivative of t squared is 2t. The derivative of 1 is 0. So the derivative of t squared plus 1 is just 2t. The high function here is 25t squared plus 125. Let's think about the derivative of that high function. The derivative of 25t squared would be 25 times 2t, which would be 50t. And the derivative of 125, again, the derivative of a constant is 0. So the derivative of 25t squared plus 125 is 50t. Now we're going to do low d high minus high d low. Low d high minus high d low. So again, p prime is equal to low d high minus high d low over what's below squared. So in this case, it's the low, which is t squared plus 1, times the derivative of the high, which we said was 50t, minus the high function, which was 25t squared plus 125, times the derivative of the low, which is what, 2t, all over the low function squared. The low function here was t squared plus 1. Quantity squared. So we have a bunch of simplification we can do here, and yeah, you're right, we could do the simplification, or quite honestly, all we need to do is plug in the number 5. So you could either simplify first and then plug in the number 5, or you could just plug in the number 5 right here. Look, if the point of the problem was to find the derivative, you would have to simplify. But the point of the problem here is not to find the derivative. The point of the problem is to evaluate it at t equals 5. It doesn't matter if you plug it into this ugly form or if you plug it into the simplified form. That's totally up to you. Plug it into the simplified form if you're comfortable with finding the simplified form of this, if you're comfortable with the algebra. Well, I'm not going to lie, a lot of you need practice with the algebra. So rather than just plugging it into this form, which would work, and you could do right now, I at least want to follow it through and do the algebra to make sure you guys understand how I could have simplified this. So I'm going to distribute my 50t through, and I'm going to distribute my 2t through. I'm going to do this in 2 steps. So I have p prime equals 50t times t squared is 50t cubed. 50t times 1, it would be plus 50t. So that's what I'm getting distributing out my first. Now I'm going to look at my second. 2t times 25t squared, which would be 50t cubed. 2t times 125 would be plus, what is that, 250t? All over t squared plus 1, quantity squared. Again, never distribute out or FOIL out that denominator. So what do I have? I have a 50t cubed plus 50t. I'd have a minus 50t cubed, distributing the negative now, minus 250t. Do not forget to distribute that negative to both of those terms. This is all over that denominator, which a lot of people forget to write, so please don't. T squared plus 1, quantity squared. Well, the 50t cubes cancel out. I'm left with, well, 50t minus 250t. So what are you getting? I'm getting minus 200t all over t squared plus 1, quantity squared. So that's our derivative right there. Okay, that's important, but that's not our answer. That's our derivative function. So what we want to do is evaluate that at t equals 5. So I'm going to do that in blue here. So at t equals 5, what would we have? We'd have negative p prime would equal negative 200 times 5 all over 5 squared plus 1, quantity squared. If your calculator gives you a fraction on this one, just hit the double arrow button. I'm getting approximately, when I look at this, negative 1.479. So what the heck does that mean? That means the blood pressure was decreasing by negative 1.479 millimeters of mercury per second. We determined the units earlier. Change in P is millimeters of mercury, T was seconds. So this is millimeters of mercury per second.